In this first video, I'm going to be explaining filters and how they are used in synthesizers and other electronics. So we'll start off first with what is a filter. Well, if you assume that you have a signal with a constant amplitude across all frequencies, you would end up with a graph like this. A filter would let you choose a point somewhere in that frequency range and start to cut away the signals past a certain point. So in this case, you would be cutting all the frequencies here, leaving the rest of the frequencies which are behind here, which would be a low pass filter, because the lower frequencies are being kept and the higher frequencies are being cut. What that allows you to do in terms of synthesizers is it lets you shape your base sound form or oscillation, which is a changing voltage or current. So there are different types of oscillations, the most basic of which is a sine wave. This contains only one set frequency going around a set voltage. But there are other types of oscillations. The other most common would be a square wave, which has lots of different frequencies over the top of your base oscillation or sine wave. So if you were to filter everything off of a square wave, you'd be left with the underlying sine wave. This is a form of subtractive synthesis. So there are two main types of synthesis. There is subtractive synthesis, where you start with a very textured signal, like the square wave there, and you remove different frequencies from it to get the underlying sound that you want. The other form is additive synthesis, which mostly uses frequency modulation, where you mix different frequencies together to produce your sound and then move them all around to different pitches when you need them. So I started looking into the basics of filters, and I started with very simple low pass filter and high pass filter. Now these both would have a set cutoff point, so you wouldn't be able to adjust them to get a desired cutoff. You'd have to physically swap components in and out to adjust them. An easy way to get around that is to add rheostats. Rheostats are a type of resistor where you can vary the resistance they have. So this here is a potentiometer. You'll notice it has 3 pins. If you ignore this third end pin, you can use these 2 pins here and here as a rheostat. I'll very quickly explain how or what these filters are. So the most basic possible filter you can create uses a resistor and a capacitor. So this would be the resistor in a circuit. So you'd have your input here, and then you would have your output coming out over here with a capacitor tying it to ground. And that is your most basic first order low pass filter. You can change the values of these in your circuit when you are building it, but after you've done that, it would then be locked into what you've chosen for those values. So to go back to this graph earlier, this is something similar to what this circuit here would give you. It would cut out some of the high frequencies, leaving only the low frequencies. I would like to quickly mention, though, when I said that this circuit was a first order filter, that refers to the steepness of the cutoff slope. So the one that I've drawn on here, this is an ideal filter. So it perfectly cuts everything past this point away. In reality, your first order would likely start to cut frequencies coming down in a light similar to that. Second order is a slightly steeper slope. Then third, fourth, fifth, and so on, until you'd eventually get close to that ideal filter. However, whilst that is very useful in terms of a musical scenario, ideal filters are not overly useful because they just immediately cut every single frequency past that line, which can remove some of the texturing. But back to this circuit, this would be a low-pass filter. If you were to swap around the resistor and the capacitor, that would give you a high-pass filter. So just to show that here, again, you'd have your input, but instead of having your resistor first, you'd have your capacitor. So you'd have your signal going through the capacitor to the output with a resistor tying it all to ground. Now, as I mentioned earlier though, this only cuts, or this has a fixed cutoff frequency, and you cannot control where it is past choosing the values of these two components. There are equations you can do to find a specific cutoff frequency when it's desired. However, I did not look into the maths of it too much at this specific point because I was more interested in getting a working demo that I would then be able to actually see working, and because I need access to a variable filter, the exact values of these aren't important at this stage. But onto how you would vary or have a variable filter. The most basic variable filter, which is passive, you would have your input signal again, which goes into a rheostat, as I mentioned earlier, which is denoted as so, going to your output with your tie-down capacitor. And tie-down just refers to it going straight to ground. And the high pass, again, would be identical, but these two are flipped. The other point I'd like to mention is earlier when I had this graph and I was talking about an ideal filter, and then I was mentioning the different orders, the way you'd construct a second order filter is almost identical to your first order filter, which I have here. However, what you do is you take your basic first order filter like so, and you take the output from that and run it straight into another identical filter. And then you have your output. So that would be a second order low pass filter, which increases the cutoff slope. And again, for a high pass filter, you would flip these two components around. Following on from that, though, with a second order filter, when it comes to making it variable, this is called a cascade filter, because you are running the first filter through into the next one. so it is cascading from one to the other. On top of that, though, when it is made variable, there is a slight requirement for the actual rheostats, because for it to work correctly, the resistances of these two components need to match. So when these are made rheostats to make it variable, they need to be paired together. And the way you'd do that is you use something called a dual gang potentiometer, which, to go back to the potentiometer, it has 3 pins all in a line, and there is a track, or you have a wiper and then a resistive track. So you have 3 pins, one connects to your wiper, the other 2 are connected by a track like this. So in the case of this potentiometer, it has a total resistance between these 2 pins of 100 kiloohms. The wiper then moves along the track, giving a different resistance between these 2 pins or these 2 pins, depending on whereabouts it is positioned on the track. A dual gang potentiometer, you have 2 of these tracks that are isolated from each other completely, and isolated wipers, which are just stacked on top of each other. So it allows you to control 2 different things with just one control. So as you can see here, this is the research that I had over the first week of my project, and I have the simple passive filters, low pass and high pass. Then I have the simple variable filters using just rheostats, where I then studied different orders of the filters and then drew out the schematics for them over here. And you'll notice when I was drawing the circuits out a moment ago, I was using blocks for the resistors like this, whereas I'm using zigzags for them in here. This is because I was using knowledge that I'd picked up at GCSE, where we denoted resistors using these zigzags. But whilst I was researching later on, I found that zigzags refer to just a component rather than specifically a resistor. So I started using the squares, which are also more common when looking at various circuits. The next thing I'd like to get onto is something called resonance, and that was the next thing I researched. Resonance refers to, or in this graph here, to go back to it yet again, this is the cutoff point. Resonance is sort of an emphasis on that cutoff point. So if you had a lot of resonance, you'd have a jump up in your signal around that frequency up to here, and then it would slope back down with the filter, like so. And I'll sketch that again just to make it more clear. So here is our cutoff point. Then we have the signal, which I'm going to start using the slope from first and second order filters. And then our resonance would come up on top like this. And you can control this resonance so you can end up with different sorts of peaks, or different heights of peaks, rather. Now, the way that you do this, or the way that you add resonance, is you actually need a feedback loop in your filter. So you'd need to take your output and connect it back round to your input. Now, you can't do it like this because this is a first order filter. So by having this connection in here, it completely bypasses the entire filter, and you just end up with your input and your output being essentially identical. So you would need to use a second order filter, like the one I have here. And instead of connecting this capacitor to ground, you'd connect it all the way around to the output. So I have it shown slightly more clearly in here. Ooh, I've jumped ahead a bit. Something I'd like to talk about very quickly before I get onto that is op amps and how they come into filtering. And op amps are a very common electrical component that are used almost everywhere, and they have many different functions. The two basic ones I'm going to talk about very quickly are buffers and amplifiers. So a buffer, you have your input signal, and it goes into your op amp. Specifically, it goes to the non-inverting input, which is denoted by a plus sign. Then you have your output is then connected round into the inverting input, like so, and then you'd have your output signal here. An amplifier is very nearly identical to a buffer. However, in the path of the inverting input, you have two resistors which are set up as voltage dividers. So I'll quickly sketch that out now. So you'd have your first resistor and your second resistor, which is tied going to ground. Then you would connect that background to the output to get your signal out. Now, the amount that this amplifier actually amplifies your input signal depends on the value of these two resistors. And the way you can calculate that is the voltage out is equal to the voltage in times by R1, R2, R2 over R1 plus R2. And no, sorry, I've drawn that circuit wrong. Let me draw that again. So you'd have your input here, your op amp, the resistor here, and then your tie down resistor here, which then goes to your inverting input, where you then have your output. And the value of these two resistors sets the gain or the amplification for that actual circuit, where the voltage out, when I say voltage out, I'm referring to the voltage going to this inverting input here, is equal to the voltage in, which is going into this resistor here. So it's coming along this wire into there, times by R1 over R1 plus R2. So this is R1, this is R2. Now, back to this, or back to resonance, you need to start by buffering your original second order filter. And the reason for that is you can get a little bit of back current, I'd guess you call it, where you can have the actual discharging of the capacitor going back and forth between the two signals. And the buffer prevents this because it essentially copies your input into the non-inverting input to the output, preventing any crosstalk, because op-amps, or the op-amps I was using, had a very high impedance, which is a form of resistance for AC currents, preventing or reducing the actual connection between these 2 points while still having identical signals. So the way you would add resonance is, as I sketched out earlier on here, you connect your output background to the first capacitor, which is what I have shown here, but with 2 buffers in between the output of each filter, so you can see it then goes all the way background to the first filter. And that would give you your amplification around the cutoff point. Now, you also want to be able to control the resonance with a filter like this for a synthesizer. And the way you do that is you'd use your potentiometer again, but instead of just using these first 2 pins, you'd use all 3 pins and you would set it up as a voltage divider. So, as I showed earlier on the amplifier, you have these 2 pins you can count as R1, and the bottom 2 pins you can count as R2. So if you had your signal going into R1, R2 would then be, or into the first pin, sorry, the second pin would then be your output, and the third pin you would then connect to ground. And that would give you a voltage divider. So rather than using an amplifier in this specific case, I'm reducing the actual input voltage going into the non-inverting input using that voltage divider. And that is how far I got with the filter in this week. So we have an input signal going into a rheostat with the capacitor tied back to the resonance over here. It then goes through the op-amp into the rheostat of the second order with the tie-down capacitor, where it's then buffered once again before going to the voltage divider, which is then buffered and connected background to that first capacitor. Now, very quickly, I would like to demo just the most basic passive filters here. So just these 4 here using a rheostat and a capacitor, or a resistor and a capacitor. So I'll quickly set those up and show you them now. Okay, so here I have a piece of equipment called an oscilloscope. And what it lets you do is it lets you visualize the actual signal you are getting. So I have just a basic square wave oscillation from a 555 timer, which I can vary the frequency of quite drastically. But I'll have it going at this relatively low speed, just so it's easy for you to actually visualize what is happening with the filters. So we'll start off by plugging our signal into our low pass filter, which we have just here. And this is a fixed frequency LFO, or low pass filter, sorry. So we should get a single signal. That's why. There we are. So you can see now that the prevailing and falling edges of the square wave have rounded off slightly. You'll notice something similar with the high pass filter. However, it's sort of the other way around. So that's the low pass filter against the base signal of the original square. Then that's the base signal, and now I'm connecting it into the high pass, which you can see there. So it now has a sharp peak and then a sharp drop-off curve. I also have the very basic rheostat-based filters, so you'll be able to actually see how the frequency can, or how the cutoff point can be varied. So the low pass version is currently set to a very high cutoff point, so you won't see any effect there. But as I slowly increase the resistance on the rheostat, you can see that the edge curves, and then I can bring it back to the straight edge, as you can see there. Now, with the high pass version of that signal, or of that filter, I've had a hard time finding a capacitor which isn't too strong. So immediately you can see that it's filtering it a lot. And when I am using the rheostat, it does make a difference. However, it's very hard to notice difference. So as you can see there is a little bit of movement. But it is very hard to get a nice clean cut with it due to the high capacitance. If I was to use a smaller capacitor, however, it would be much easier to get the slightly nicer signal. So I'll just demo that again quickly. It even goes so far to cut out the whole signal from that oscillation, leaving me with just a base voltage. And then you can bring it back in as shown there. Back to the active version. Unfortunately, I did not have the components with me necessary to actually build a prototype of it on the breadboard to then demonstrate to you. However, I do have a synthesizer with me that uses a very simple or very similar filter, so I'll demonstrate that now. Okay, so here I have my synthesizer. It's a Korg Minilogue XD. This here is a little built-in oscilloscope, so I don't need to use the large one to demo this. But here is the basic square wave from one of the oscillators. And again, I then have a low-pass filter here. However, it seems to more decrease the actual volume when appearing on here. In reality, it is giving the curve that you were able to see with the other oscillator. And then I'm now going to add in resonance, so you'll be able to see how that visually changes it. So as you can see, the wave starts to tremor a bit, and you start getting these little peaks at the bottom and the top of the prevailing edges. As you increase it further, you can start to see that it actually ends up with an oscillation along the top and bottom of the waveform, and it keeps going until you can make out the shape of the square wave, but there's an entirely new oscillation on top of that original signal, and then you can bring it all the way back to the original and all the way to the resonated frequency. This concludes the first week of my research on filters, which is working towards my first milestone of designing and then prototyping a filter. In the second week, I'll have that up shortly as well, where I'll be looking even more into filters and the different types or ways of filtering.